So we'll take a look at chi-squared, another use of chi-squared, which is a test for homogeneity. And really, what you're looking at, it's used to determine if choices are um, distributed the same among groups. So here's the idea, just the breakdown of the word, right? Homo means same. So you're looking at, are things evenly distributed among different groups? So our null hypothesis here will be that the distributions are the same among groups, and then the alternative to that will be that the distributions are not the same. Oop, excuse me, are not the same among the different groups. The conditions for us, again, we want randomness. That's important. All right. So typically, again, taken from like a simple random sample, or somehow they've interjected some type of random selection in there. And then we want to make sure all of our expected values are greater than 1 and no more. If we do have a small expected value, we want to make sure that no more than 1 out of every 5, no more than 20% of expected values are less than 5. Now, just like we saw before, both conditions 2 and 3 can be accounted for if all of our expected values are greater than or equal to 5, which is typically the case. So really, if we know that it's random and all expected values are greater than 5, we're in good shape. The degrees of freedom for this particular chi-squared test is a little bit different. We're going to end up with matrices, so it's going to be the rows minus 1 times the columns minus 1. And what you're going to see, we're basically going to end up with two-way tables for our data, and there's categories that everything's falling into. So our best bet with this one is to run some matrices. So we'll go ahead and we'll take a look at one particular example. So let's say that we did this random sample of 2006 college graduates and kind of figured out what was their plan for postgraduate activity. So you can see we got different number of people within each school, whether it's ag student, art and science, whether in engineering or social sciences, and then just kind of breaking down, all right, what is their plan after school? Whether they were going to go get a job, whether they went to grad school, or whether they did something completely different. What that might be, we don't necessarily know. But what we can do is using this information, we can go ahead and fill in some totals. 379 plus 305 plus 243 plus 125. So there were a total of 1,052 students that ended up getting a job right away. 186 plus 238 plus 202 plus 96. 722 of these students attended grad school. 104 plus 123 plus 37 plus 58. 322 of those surveyed did something a little bit different. Now it's going to be helpful if we can go ahead and get the total number within each group. So we have 669 agriculture students. There were 666 that were in arts and sciences, 482 that were in engineering, and then 279 social sciences. So what we should notice is the biggest group that responded to this survey, or that were selected in this survey, were the agriculture students. So what we would do is we start to look for expected values. We'd expect some bigger values for the agriculture students because there were more of them in the group than maybe the social sciences. Now, overall total is also going to be important to us as we start to figure out what our expected counts are. Now, there's a long way to go about this, and the formula to come up with an expected count would be the row total times the column total, and you're going to divide by the overall n. And again, here's your overall in right here. So, in other words, a student that was in agriculture that got employed right away, to calculate that value, it'd be 1,052 times 669 over the total 2,096. Now this could be a tedious process because we have 12 different pieces of this table to fill in. Well, what's nice for us is actually the calculator will do it for us. If we will run a chi-squared test, if we'll put the original information in for matrix A, so we're going to take the observed values, and this is going to go into a matrix. And that's going to go into matrix A. And what we'll actually do is, for this to work out well for us, we're actually going to go ahead and run our chi-squared test for homogeneity. And something we can think about. So degrees of freedom very quickly. So there are 3 rows. So that'll be 3 minus 1 is 2. 4 columns. So 4 minus 1 is 3. So we have 6 degrees of freedom. And once you put that data into the calculator and actually run the test, what you'll notice is it'll ask you the observed in matrix A, and then it'll say expected for matrix B. But we haven't actually put anything into matrix B. But what's nice is the calculator is going to run this for us. And then if you go back and you take a look at matrix B, all of a sudden data has been put into matrix B for you. Well, sure enough, what you're looking at are the expected values. So we expect 335.8, about 336 ag students to go out and get a job right away. So we're a little bit higher than that expected value. We expect 230. We expect 230.5, so about 230, 231 to go to grad school. Again, this time we're a little bit lower than that. We expect to see about 102 or 103, and there we go. That one's pretty close. So you keep kind of picking through this information, and what we'll see, some values are very, very close to some of the observed values are very close to the expected, and then others are pretty far away. So for example, the one that I'm writing right now, right, we expected 74 engineering students to do something different, whereas in fact only 37 of them did. And then that final piece, 6.1, and then 42.9. So what you're looking at here in terms of the matrix, so matrix B is your expected, those are the expected values. Now, as you do these problems, it is expected of you to go ahead and jot that expected matrix down. And the big reason there is because as we set up our conditions, we want to make sure that we can justify that we do in fact have all expected values greater than 5. And the fact of it is, if you look in your table, that is definitely met. And then random, we're going to have to assume that these were randomly selected students. Never actually said. So the biggest reason, again, we can justify this statement, all expected values greater than 5, because we write down the expected values matrix. So make sure that you do that each time you do a problem like this. All right, so let's go back and look at the null and alternative hypothesis. So here we would expect the distribution of choices to be the same between colleges, and then the alternative distribution of choices to be, is not the same among the different colleges. So we'll drop our chi-squared. So again, it's a summation. We've got the observed values minus the predicted or the expected values squared over the expected. Go ahead and just put one of them in there so we know we can justify that we do know how this formula works. So I'll just pick the very first one. So we observed 379 agriculture students that got a job minus the expected 335.8 over 335.8, and then at that point let's just go ahead and get the actual chi-squared value, which is 54.5, which gives us a pretty small p-value, and really it's to the point where I'm pretty comfortable saying that's essentially zero. So it does look like maybe there is a difference depending upon what school you went to that might affect what your next plan, what your next step is, whether you need to go back to school, whether you get a job right away. And really common sense would dictate that, yeah, typically certain career paths, some you get right out of school, you go right to work. Some, well, you go back to grad school. You almost need that degree. So for us, we can see right away that we're going to reject the null. And so it appears that the distribution of post-grad choices is not the same among the different schools.